Hi there, my name's Brent, and along with me are Brittany and Isaac. We are Team ME59, and our project is the optimization and development of an alternating pressure mattress pump. Our faculty sponsor is Professor Ying Li, and our industry sponsor is Andy Shepard. We'll begin by looking at the project's background and deliverables, then viewing the analysis and final design, finally looking at our results and wrapping it up. Our project was started by the Unisoft Medical Company, who wanted us to design and optimize a pump for their alternating pressure mattress, which is a multi-cell, single-use disposable medical-grade mattress. The deliverables for the project were a rapid inflate capability of 15 minutes or less, the ability to run on DC power for future mobilization, programmability for pressure optimization, and a user-friendly interface. Isaac will now discuss the analysis.
It was important for us to conduct a flow analysis of the system to get an idea of how the system will react to different parameters. On the left, you can see a graph of pump flow rate versus its outlet pressure, which we needed to access for subsequent calculations. A loop was created to iterate over these values of the pump flow rate. During each loop iteration, the outlet pressure for the first valve can be calculated by rearranging the relationship shown on the right, where the value of P1 for the first valve is the outlet pressure from the pump. This same idea is then extended to the next valve, where its inlet pressure is the outlet pressure from valve 1. Finally, after calculating the pressure drop in the system tubing, the total system pressure drop can be obtained. The main takeaway is that the lower the amount of valves and the length of tubing in the system, the lower the losses in the flow will be. We had an issue with the initial valves that we bought because they were restricting our inflation time. In order to justify the purchase of larger valves with a higher flow coefficient, we ran the MATLAB script with both valves and compared the results. The figure on the left shows that for a given flow rate, the pressure drop across the larger valve will be much lower. This relationship becomes more drastic at higher flow rates. In order to improve the flexibility and yield less flow restriction and pressure drop over our current design, we've redesigned the system according to the model shown here. The main benefit here is that the valves are in parallel instead of series, allowing the air to flow through 2 valves instead of 3. The controllability is also improved in this design since all 3 cells are independent from one another. In our old design, either cell A or cell B could be inflated, but not both simultaneously. During the inflation routine, the air will first flow through the body, then cell A, and then cell B. The alternation routine will then begin. A small example of the ladder logic that the PLC uses to control the system. The complete program consists of 39 rungs of logic, and extensive testing was done to ensure that the system does not fail or act incorrectly in any of the vast amount of possible scenarios. The purpose of the logic is to control the pump during inflation and alternation, as well as to monitor the pressure sensors and make adjustments as necessary. Now Brittany will discuss our test rig.
This slide shows our final test rig, which includes an AC-DC converter, a pump, 2-way and 3-way valves, manifolds, pressure sensors, and the PLC. The PLC on the left is the brain of the system and has all the ladder logic code downloaded into it. It has a user-friendly interface that anyone can use. First, it will display a startup screen letting you know that it is preparing the mattress. When ready, it will display this screen. When paused or pressure is outside the range, a message will display at the top. If the pressure is too high or too low, the system will correct itself and return back to the in-use display screen. Now for our results. We have concluded that the CV values act like resistors and flow rate is directly proportional to the CV values. Therefore, valves with larger CV values are ideal for this system in order to meet the rapid inflate requirement. Most of our testing to date was fill time tests and development of a robust ladder logic program. As you can see on the right in the table, we tested the fill time with various components to see their individual impact on the fill time. The overall fill time was 12 minutes and 15 seconds, which meets our goal of 15 minutes. For the ladder logic testing, we used potentiometers to mimic the pressure sensors so we had more control over the pressure input. This allowed us to run through various scenarios that could happen with the patient on the mattress. For example, if the patient's family member came to visit and joined them on the bed, the pressure would spike. We had the program react to this by displaying a warning and adjusting the pressure to be back with ideal parameters. We also added in a pause alternation function so patients could press this button when they have visitors on the bed and they are up and out of bed for various reasons. In terms of meeting our objectives, we are confident our project was a success. It meets the inflate time requirements, the PLC interface is user-friendly, the ladder logic is robust and optimizable, and all components are DC so the pump can be mobile in the future. We suggest that Unisoft or future senior design teams continue testing and optimizing pressure parameters. We also suggest an ECE or CSC team is used in the future to write a dedicated program in order to eliminate the need for a PLC. Once the system parameters are optimized, a cost analysis and downsizing could be done to reduce the cost of a production pump. We are Team ME59. Thank you for watching.